Let's welcome our last speaker in this aerospace section. We are very glad to have Professor Hesham to be here to give the talk in person. And Dr. Hesham is an assistant research professor with the Collaborative Research Center of Excellence for Aeronautics and Astronautics, which is the joint scientific effort between KACST and Stanford. And today's presentation is runtime assurance via real-time generation of trajectory and transverse dynamics regulation law. So Professor Hesham, the floor is yours.
Great, thank you so much. Good afternoon, everyone. I wanted to give a special thanks for everybody that contributed to the organization and coordination of the conference. I'm honored to be talking today about runtime assurance via real-time generation of trajectory and transverse dynamics. So my talk is actually divided up into two parts. So the first part, I want to give everybody an introduction about KACST, Joint Centers of Excellence Program, and the Center of Excellence for Aeronautics and Astronautics. Some people may be their first time visiting the kingdom, so I thought this could be an opportunity to present about that. So once again, my name is Hesham Shageer, and I'm here representing the Center of Excellence for Aeronautics and Astronautics. So just a little bit of history about the King Abdulaziz City for Science and Technology, also referred to as KACST. So it originally was established in 1977, and the initial goal was to be Saudi Arabia's National Center for Science and Technology. So the underlying objective was to promote the awareness of science and technology within the public. So it's interesting how KACST evolved over the years, that this became a research center, and then eventually evolving into what it is today as the National Labs. So over the years, KACST also has acted as a Ministry of Science and Technology, and similarly in the US, where they have the National Science Foundation. And so KACST has been involved in space missions and designing of technologies, as well as in helping certain challenges within the kingdom. So an interesting fact about KACST, that it's actually an incubator for different government agencies that are related to science and technology. So over the years, for example, like the ICT ministry, so over the years, as the sectors become mature enough to handle, for example, an authority or a commission or a ministry, then these new agencies will be formed. So for example, SDAIA, the Saudi Data and AI Authority, the MCIT, which I had mentioned, as well as the King Abdullah City for Atomic and Renewable Energy. So these different entities that relate to science and technology actually were incubated within KACST until the sector became mature enough to become an actual government agency. So a brief overview about KACST in terms of how it's formed. So it's made up of research institutes, national centers, as well as research programs. So as we can see here, there's 8 main focus sectors that KACST works towards: space and aeronautics, digital technologies, healthcare, defense and security, as well as many others. So some of the consultation and other projects that KACST has successfully completed, over 100 consultation projects, as well as national projects. So KACST currently has nearly about 4,000 employees, so 2,000 of which are researchers, and 1,000 of those are actually PhD and master level holders from top universities throughout the world. So now, talking about the Joint Centers of Excellence program, which is one of the premier initiatives within KACST. And so this program was actually established in 2013. And the main objective of the program is to create a bridge between KACST and top-tier universities in order to allow access of scientists and researchers to know what's going on in cutting-edge technologies. So at the time, there were scientists and researchers maybe working on topics that had already been completed or that were furtherly developed throughout the world. So just briefly about the JCEP, we call it JCEP, the aspirations that we have. We want to be a highly sought after program in research, development, and innovation. So our vision is to create world-class collaborative research centers. And our mission is to provide a venue for researchers and scientists to work collaboratively on emerging trends as well as national interests. So the strategic objectives we have within the program is to provide cutting-edge training programs, to produce research and IP, and more recently, we're looking into how we can commercialize these technology developments, in addition to expanding to more local partners and stakeholders. So currently, JSEP is formed of 13 joint centers, 11 of which have academic partners, and 2 are with industrial companies. So the underlying objectives of the program, like I had mentioned, is enabling access to cutting-edge knowledge, in addition to establishing international alliances. So just to give you a flavor of the different centers we have, for example, with MIT, Center for Complex Engineering Systems, and a center we have with Oxford, focusing on petrochemicals. And each one of these centers actually falls underneath a theme. So this themes, we've kind of grouped the different centers to know more about which themes they fall under. And as we can see here, within the space and aviation sector, we have 3 centers. In emerging digital technologies, we have 4. And these centers are actually spread across multiple sectors. So for example, the MIT Center works in both in clean energy as well as emerging digital tech. So how we measure success within the program, we look to produce research outputs, human capabilities development, as well as community outreach. So the research outputs, we focused mainly on conference and journal publications, and these are done collaboratively with the partner. In human capabilities development, we look to get our researchers accepted at top tier universities, so focusing maybe on top 10 or top 20 schools throughout the globe. And more recently, we've been reaching out and participating in co-op training programs for high school students, as well as global competitions that relate to science and technology. Some of the success stories we've had within the program, so nearly 200 researchers and scientists placed at top-tier universities, as you can see here in MIT and Michigan, as well as over 400 joint conference papers and publications, in addition to patents. So the Center of Excellence for Aeronautics and Astronautics, which I'm a part of, it was established in 2014. The initial focus was on emerging frontiers in research and innovation related to space and aviation. And this partnership is actually with the Aeroastro department at Stanford, and it involves faculty, senior scientists, postdocs, as well as graduate students. And from the KACST side, we have, for example, like myself, assistant research professors, engineers, researchers, and scientists. So throughout the center, we have multiple research projects that we work in collaboration with Stanford. So these are just some examples of some of the projects, and I'm just going to go over quickly kind of the historical projects that we've completed. So one of the interesting projects that was completed was the MGRS, which is the Modular Gravitational Reference Sensor, which was actually flown on a space mission, the UV-LED, in 2014. And there was a big data set that was collected, and even today, we're looking for ways to benefit from that data set. And other projects that relate to aerospace, as well as computational dynamics for aircraft design. So we've done flight testing as well as technology design. So now kind of shifting gears into the second part of the talk, where one of the projects within the Center of Excellence and some of the motivation for this topic is for path planning for autonomous systems. So these 4 applications we found to be kind of the spotlight that we've seen in the literature in terms of what people are interested in that could benefit from path planning. So the first example we've seen a lot of speakers talk about today with self-driving cars, as well as multiple UAV drones with the drone racing. And we have some preliminary results with our partner from Stanford, with Marco's group, where we've done some simulations of assistive free flyers on board the ISS. And I think an interesting topic that maybe people don't realize initially, that with additive manufacturing, there is path planning involved. So we're looking for ways to expand to multiple applications. So talking more about the motivation here, being able to guarantee safe and efficient operation in the presence of obstacles. Some of the challenges we've seen for example, with the AstroB, where you have a higher order nonlinear system with non-convex constraints, and you want to ensure that there's no collisions with obstacles. So the approach we've adopted in this research is to have both transverse dynamics as well as what's known as a guaranteed sequential trajectory optimization, referred to as GUSTO. In addition, we want to guarantee a runtime assurance in combination with our design. And this just shows an example of manipulator in space that could benefit from such a planning algorithm. So just an intuitive kind of approach here to explain what the trajectory planning and control and how it works. So we have our plant in addition to the environment and where the plant is. So we want to extract the system states, and we want to feed this back to our control law, in addition to our regulation law, which we're calling here our runtime assurance, and finally the trajectory planning. So the trajectory planning is both done in a path generation system. So looking inside our runtime assurance module, we want to guarantee safe operation of our trajectory planning. So the way the system works, we have two separate trajectories that the system could follow. So we generate safe trajectory forecasting. So from these trajectories, we decide based on our assurance policy whether we want to switch to the not fully trusted advanced trajectory or maintain the safe forecasted trajectory, which is done through the transverse dynamics. So going into how the formulation of the trajectory is done, so we first define a cost function. So this is taking into consideration the final time as well as the obstacle penalty, and we could expand this to include more constraints. Next, we solve for our XR of K, our reference, as well as our nominal control. And this is done in a discrete format. So now once we've done our trajectory generation, now we're ready to set the stage for the transverse dynamics. So this is done by parameterizing XR with an arc length S, which then creates our time series. Here we define it as S of K, such that in the beginning of the trajectory, our S of 1 is 0, and at the final state of the trajectory, we have our S of capital N equals the total length of the reference trajectory. And here, XR of S is fitted using spline functions, and our nominal control is defined as such. So the mathematical formulation we've created for the transverse coordinates, here's an example of how this could be built upon a reference trajectory. So first we define our system dynamics, and this is a general definition here with state variables and control inputs. Then we do a transformation to the transverse coordinates. And I think this illustration shows how, it's a good illustration of how the relation of the normal plane, as well as the point on the trajectory, as well as the dynamics of the transverse coordinates. And here, the set of orthonormal basis vectors is a sufficient but not necessary condition that we have at each S, where T is the tangent vector. And here, this is a transformation. The O of S is a transformation of our state vector, rho. So once we've defined our transverse coordinates, now we can define our we can formulate our transverse dynamics. So once again, this is here in the 2D plane of the normal plane, what I had showed previously. So just looking at the still image of the 2D plane. So here we define our dynamics as the motion along the trajectory. So I'm going to read this here quickly. So this is a good way of understanding what transverse dynamics is. So it's a dynamical system that describes the evolution of the system state relative to a reference trajectory, analogous to basic kinematics. Here we can describe transverse dynamics as the velocity of a particle in Rn relative to a moving frame. So Professor Betchet actually had a good explanation of this in his talk earlier. So I'm not going to spend too much time talking about this here, but just going over it again quickly. This was developed actually in collaboration with Marco Pavoni. which is known as the guaranteed sequential trajectory optimization, which is based off of the sequential convex programming. So the idea behind SCP is to solve a sequence of convex problems that stem from successive linearizations. So the interesting example that I wanted to present here is how the Gusto code could be used, or how it's been used for trajectory of a quadcopter. So the interesting way that Gusto works, that you give it an initial trajectory. Here it could be a straight line. And then as you run additional iterations here, you can improve the trajectory by linearizing around each new trajectory. So starting with a straight line and then iterating to improve the trajectory of each additional trajectory. And this is another simulation that we've performed using the AstroB, and we managed to have actually the environment of the International Space Station. So we've worked with Marco's group in the past to actually test some of these algorithms on board the ISS. So we hope in the future that we could actually test these algorithms in space. So although these results are preliminary, we have an illustrative example that we wanted to share with everybody today. So this is a simple kinematic system where we have our x dot, and our x dot here is a three-state system. So given an initial condition and a reference trajectory, as well as a nominal control. So this example shows how our transverse coordinates are moving along a trajectory. And we show different initial states and how they all converge to our reference trajectory. And here on the upper right corner, it's more of a legend to show the different space. So these are trajectory tracking examples. And here we show the 2D normal plane in the bottom half. So as we can see here, initially, we start far away from the reference trajectory, and we quickly converge. So another example we've been working on is obstacle collision avoidance. So here we've shown an example without the runtime assurance to show how our trajectory forecasting actually shows that there is an unsafe trajectory that it wants to follow. So as you can see, the trajectory passing through the obstacle here. So to overcome this, we have our runtime assurance to calculate the future trajectory and determine whether it's going to be safe or not. So in this case here, where the blue line represents just a random path that the robot is on, and we want it to reach to our recovery state. And so we follow the trusted transverse dynamics generated trajectory. So I'll run this simulation one more time. So as we can see, as the robot follows a random blue path here, it's looking for different trajectories in order to avoid the obstacles and reach the endpoint in an optimal manner. Great. So this is what I had prepared for today, and I wanted to give a special thanks to our team. So Eric is actually one of our team members, and we have our team here, Ibrahim and Umar, Abdulaziz and Fadl, Fatima and Hani. She's actually a student here. I think she's going to be arriving tomorrow. So thank you, everybody, and I'm honored to talk about our research, and I'll be happy to take any questions, even general questions about KACST or.
Thank you so much, Professor Hesham, for sharing this interesting talk and your ambitious projects. So are there any questions from the audience?
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Thank you so much, Professor Hesham, for the interesting presentation. I'm Ripto Muktiwibowo. I'm from King Abdulaziz University. I want to ask about can you explain about the knowledge and technology transfer and joint pattern in KACST. So because I need to know how to join and collaborate, maybe we need maybe at the next time we can join our collaboration. Thank you so much, bro.
Oh, you're welcome. Thank you for the question. So the way the Joint Centers of Excellence program works, that we have agreements with each partner. So these agreements could be either a collaborative research agreement, or it could be a collaborative research and training agreement. So within this agreement, we mention, for example, like percentage of IPs owned. So IP ownership could be 50-50. And we also, like more recently, we're trying to spell out in terms of what type of training activities we expect from the researchers and scientists. So for example, spending time at Stanford, so 2 months, say 4 months a year in 2 different 2-month visits. So the technology commercialization, there is some examples where we have startups. So there have been startups that have been created from technology that was developed within one of these centers. So some of the challenges I've seen within those is actually operating costs. So for example, you have to pay for patent registration, and you have to pay, obviously like employees and things like this. So these are one of the challenges we've had in terms of creating a startup is one thing, but operating the startup and, is it relevant to the market here in Saudi Arabia? It might not be, right? So the market could be in the US, the startup could be there. But I think one of the challenges we've had is, like I mentioned, just being aware of what costs are required for a startup. So the registration of the patent, these are fees that you could split with the partner. And I think, like I said before, that we at KACST are also looking to expand more into commercialization of technology. And I think one of the interesting talks, like what the Aramco researcher presented, is to actually select projects that are relevant to the industry. So in the past couple of weeks, I've realized that the project selection is maybe one of the most important parts of running a research center. So whether you select your projects from industrial challenges, or they're theoretical challenges, or they're from curiosity from the researchers. So we're looking for ways to try to mesh these together, where industry partners are interested in our work at the same time, the researchers and scientists are excited to continue working on topics. I hope that answered your question. Thank you.
Thank you very much, Maxime from X-Wing. You're going to see a trend in my questions about how do you run those algorithms in real time, and can you have certifiability for those algorithms? When I say certifiability, is having the regulator to approve and to have the DO-178 process around it. So do you think your algorithm can expand to run on a small processor? And also, do you have assurance that you're going to be completing your real-time assurance in a fixed period that can be very short?
So yeah, this is a great question. I think this is one thing that we always, the first thing we look at in terms of how this could be implemented on board electronics. So we have done some demonstrations at Marco's lab, where he has a 2D table, and we can have some of these robots communicating with each other. And we actually spent some time with the researchers. They could tell you more about this, where, like you mentioned, the iterations. So what's the time that it takes for you to complete the iterations? So there is different methods to reduce this time. So I think this is something that's still kind of an open research topic in order to be able to process things quicker. But we have done some preliminary tests with the Gusto algorithm, and it has worked on board hardware.
Thank you.
Great, thank you.
Thank you, Professor. Just a general question about KACST. So other than the aerospace and aeronautics applications, what kind of other robotic projects do you have there?
Interesting. So we have actually one of our other researchers here. So she has a talk, I believe, after tomorrow. So there's other centers within our ICT Institute that focuses on robotics. So the one center, like I presented today with Stanford, does have examples of robotics, but I think maybe you'll have to wait a couple of days, and she was going to present some more work that we have at KACST that relates to robotics. So hopefully, well, we'll give you, we'll make you, now you have to come to the next talk.
Thank you.
Yeah, you'll have to wait to see.
So thank you, Professor Hesham, for attending this conference in person.
Thank you.